up till now, you have learnt that there are 360 degrees in a circle. And that 360 degrees is really arbitrary. Someone just decided that this is a 90-degree angle. There's 360 in the whole thing. Maybe it's somewhat connected to there are 365 days in the year. And the sun or the earth travels around the sun. Originally, people thought a circle. Now it's like, oh, it's a little bit of an ellipse. But it's like, hey, so let's do 365 degrees in a whole circle. And they're like, oh, but the math is ugly. Because that would be like 182.5 degrees in half. Oh, and what about leap years? Oh my goodness. So if we do 360, it kind of is somewhat nice, but it is arbitrary. So today we're going to learn about a radian. And a radian looks like this. If we have a circle and we draw a radius, and I'll draw it here in blue. And I took a piece of string and I cut out a piece of string exactly this length as the radius. And I started that string and I bent it along the edge of the circle. Whatever this angle is cut out is called 1 radian. 1 radian is when the arc length, and we were doing formulas for arc length yesterday, when the arc length is exactly the same as the radius, that's 1 radian. And they found out that this angle doesn't matter how big or how small a circle that you have. If you measure 1 radius around the outside of a circle, you get the same angle no matter how big or how small that is. So now, how big is 1 radian? Well, what I have here is an equilateral triangle. It's a little bit bent from time, okay? An equilateral triangle, you know in degrees, what are all the angles? What would they be equal to? Well, all of them add up to 180, and then one of them would be 60, 60, and 60, right? Now, if I take this equilateral triangle and match it up on here, I need to make my circle a little bit bigger to make it perfect. What I could do is, can you imagine bending that side to be perfectly around the edge of the circle? And if I push down and bend that side, do you see that this angle, as I push down, that angle would go 60 and would go a little bit less? So here is our very informal definition of a radian. 1 radian, a little less than 60 degrees. That's our visual. Does it make sense as I bent that? That this angle would get a little bit smaller because I have to bend it so it matches up to the edge of the circle. So now we have a visual for what 1 radian would be. It's always going to be a little bit less than 60 degrees, although we're in pre-calculus class. Okay? In pre-calculus math, you're used to being exact. If someone said, what's the answer? I don't know, 5-ish? You'd be like, what? You can't write 5-ish on a test. Somewhere between 10 and 20? I don't know. Like, we like to be exact. We're like, oh, I can go to 3 decimal places. So a little less than 60 doesn't make us feel very good. But we can figure this out. Okay? The question is, if you started cutting out these strings and one of them went to there, the question is, how many radians would there be in the whole circle? So I cut off another one, and I cut off another string, and measured another string, and another string, and another string. Okay, oh, all right. There are 6 and a bit. 6 and a little bit radians in a whole circle. Okay, again, I hope you feel a little bit like this is not very accurate right now. But if I actually measured strings around, I would get 6 and a bit. But when we're measuring things around, we already have a formula for that. What is that called when we measure the whole edge of the circle? Okay, the perimeter, what's the perimeter special name for a circle? Circumference. And you might not have known this, but some of you, I saw it already in their examples, some of you were mixing up your area of a circle formula and your circumference formula. Because they're very similar, right? Area is pi r squared. It's got a pi, it's got an r, it's got a 2. Circumference is 2 pi r. It's got a pi, it's got an r, it's got a 2. Oh my goodness. One's got a big 2, one's got a little 2. How do I remember? Okay? So we already know that our circumference is 2 pi r. In our circumference formula, what does the r stand for?
Radius.
Radius. I'm going to put the 2 pi in brackets. How many radiuses does it take to go around the whole circle? 6 and a bit. That's this formula. The circumference is, what is 2 times 3.14? 6 and a bit. Right? 6.28 is it more, sounds more accurate now. 6.28 radians in one circle. So more exact, there are 2 pi radians in every circle. Doesn't matter how big or how small the circle is, it's 2 pi. And this is why radians are considered a better measurement than degrees. Degrees are arbitrary. Radians are based on a measurement. They're based on the length of the radius. And so because it's based on something else, it has meaning. Whereas degrees are just arbitrary, someone decided. There has to be 2 pi radians in a circle. Okay, now this measuring around a circle, historically it has a beautiful history. Like, people wanted to notice that no matter how big or how small, there was a relationship not only between the radius but between the diameter. And in fact, this is where pi came from. Oh, I'm gonna get off topic here. Give you a little history lesson. Okay, so we'll come back to this note, but I'll start a new page. Draw a new circle. There we go. Draw a diameter. Okay, there's a diameter. So if you cut out strings with diameters, well, then you would get exactly 1, 2, 3 and a bit diameters. Just like I got 6 and a bit radiuses, does it make sense that I would get 3 and a bit diameters? So mathematically, historically, people noticed that no matter how big or how small a circle was, there always seemed to be the same amount of diameters around the edge. Early mathematicians were like, it's okay to be close. So you can see in some mathematicians' work, they said 3 is close enough. 3 is obvious, like it's off by quite a bit, but 3 is close to enough. So then the question is, how do we find it exactly? How do we find out this number exactly? And we'll go back to a mathematician called Archimedes. Archimedes is the first mathematician that got really, really close. Other mathematicians had come along and said, I think it's 22/7. Anybody have a calculator? What is 22/7? That's 3.14287. Is that about it? That's exactly it? Okay, good. So, what's pi? 3.1. Oh my goodness, it's off a little bit. 3.1415. But 22/7 is pretty darn close. So a lot of people thought maybe this is the right number. Maybe we should just use 22/7. So Archimedes comes along and he says, you know what I'm going to do is I'm going to find out what this number is. And I'm going to use the following technique. Because nobody can really measure around a circle. We have no formulas for that. But Archimedes, this is like 300 BC. He's working on this with math stuff. They have formulas for triangles. And so he says, I'm going to take this circle and divide it into 6 equal sections, making these triangles like this. 6 equal sections. Okay? And I have the math that I can figure out what this length is here, 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 and here. And in degrees, if you did 6 equal sections, you see he's made a 60-degree angle. And if the radius is 1, then this makes an equilateral triangle. Those will all be 1. And if you traveled from here to here, and then here 2, then 3, then 4, then 5, then 6, then he would have been able to say that I guess I'll say my circumference has to be bigger than 6. Agreed? And we know now it's 2 pi. My circumference would be 2 pi, 6.28. But Archimedes says it's bigger than 6. He also had the skill at any point along here to draw tangent lines. And he was able to figure out the distance from each of these. I'm going to just estimate it right now. It's actually he did a lot of intense trigonometry. And he figured out maybe that's 6.5. So he now knows that the answer of 6.28, it has to be somewhere between 6 and 6.5. That's where he started. And this is where Archimedes uses something that he called his method of exhaustion. Does that sound like a fun math thing to do? The method of exhaustion works like this. He said, well, any line that I have the mathematical ability to cut it in half. So if I take each of these 6 sides and cut it in half and draw a line and connect a new point, now I can draw a 12-sided. Oh my goodness. When you draw a 12-sided thing, isn't it really close already? If I draw a 12-sided shape, it's pretty close to a circle. I will, has anyone seen a Canadian $1 coin? They're called loonies. Or do you guys just all tap from that? No cash anymore? Anyways, next time, if you ever do see it again, next time you see a loonie, it's actually not a circle. I know, I'm blowing your minds right now. It's the only Canadian coin that's not a circle. All the other ones, quarters are circles, dimes are circles. Pennies might not be. I have to check a pen. You got a loonie there? Mm-hmm. Has it got 5 sides to it? Yep. How many sides does it have? Does anyone know how many sides a loonie has? Because you thought it was a circle.
Is it 12?
It's not 12.
10.
It's 11.
What's that?
It's like messed up. There's 11 sides to a loonie. It's not a circle, but already at 11 sides, some of you are like, what? It's not a circle? Some of you are like, this is news to me. I always thought it was a circle. I learned something today. Like you should be learning something every day in pre-calculus, but I learned something important today. But already at 12, it gets pretty close. So Archimedes did 12 sides on the inside, 12 sides on the outside. You know what he did next? Cut it in half. 24 on the inside, 24 on the outside. Oh, I could get closer if I cut it in half. 48 on the inside, 48 on the outside. He ended up doing 96 on the inside, 96 on the outside. When you see a 96-agon, that's a perfect, like a hexagon is a perfect 6-sided shape. If you have a perfect 96-sided shape, you call it a 96-agon. It looks so much like a circle you can't tell. And he's like, well, if I wanted to go closer, I could do the hours and hours of math to figure out doubling 96 and 192-agon and figure that one out. You could do that all the way. So what Archimedes says is he was the first to say I can get as close to this number as possible. and I don't remember if he got like 6 decimal places correct, how many decimal places he got correct. But he was able to say it's between this fraction and this fraction. And then I got closer between this fraction and this fraction. And he said if you keep doing that forever, you could get as close as possible. In fact, the pursuit of finding pi has existed for a long time. And it's actually one of the ways that they measure how fast computers are. Like you ask a computer, okay, computer, can you give me 1 billion digits of pi? Go. That takes some time, right? Right? And faster computers can give you those 1 billion digits of pi quicker than another computer. But then mathematicians have also looked at, here's Archimedes' method. It's slow. Maybe there are some other methods for, oh, I'm really getting off topic today. We don't have time for this. Infinite series of pi. Here we go. Here's some famous ones. This is crazy. If you do 1, okay, you ready for this? This is a really simple pattern. If you start with 1, subtract a third, but then add a fifth, but then subtract a seventh, but then add a ninth, but then subtract an 11th, and then add a 13th. And you keep going for as long as you like. Whatever answer you get, multiply it by 4. And if you go forever, you get pi. Isn't that crazy? 1 minus a third plus a fifth minus 1/7. We could even, I'm sorry, this is interesting math. I should not be wasting your time. 1 minus a third plus a fifth minus a seventh. When do you want me to stop? Yeah, I hear you. You're like, keep going all class, Mr. JR. Smarties. Right? If I stop at 11, I'm at 2.97. If I didn't stop at 11, if I added 1/13th, well, I'm now at 3.28. And if I keep going and keep going and keep going, I get closer and closer and closer and closer to pi. Right? I was 2.97 is too low. 3.28 is too high if I do one more. Now I'm at 3.01. If I added the next one, I get too high, and then I subtract too low, then too high, and I keep getting closer and closer and closer and closer. And if you did this forever, you could get close to pi. Yes.
Where'd the concept of pi even come from?
It came from the circle.
Yeah, I know, but like
the concept didn't come from anywhere. People said, how many diameters does it take to go around the whole circle? And we get closer and closer and closer, and this number that comes out is what we call pi. But it is an irrational number that goes on forever without a pattern. It's in fact even a special kind of irrational number called a transcendental number. Mathematicians have proved that there are an infinite amount of transcendental numbers, although in our real life, we've only found a handful of them. Pi is one of them. We're going to learn about another one, E, later on in this course. And they're super important, and they unlock a whole bunch of meaning in the world, but we've only found a few of them. Who knows, maybe someone's going to find in the next 100 years a new crazy number that explains a whole bunch of the universe.
Why is it called pi? Was there like a guy named Pi?
It's a Greek letter. I don't know who decided on calling it pi. Probably is in this lovely book that I have called Pi. This is a book all about pi. Interestingly, on the very first page, all those tiny things, those are numbers. And it has numbers, little tiny numbers on every page until you get to the very end. And did you know that the 1 millionth digit of pi is 1? There's also some really crazy, I think like the 360th digit of pi is a 6, but right before it's a 3 and right after it's a 0. Like, what?
Why do we
What?
find like every single digit of pi?
Why or how?
Like both, I don't know.
Well, because it's a number that goes on forever with no pattern, it gets intriguing to try to figure out what are the next numbers.
Wait, so what's like the highest digit that we know?
We know quite a bit because now that we have supercomputers, you could find like that one has 1 million digits just in that book, right? And then, there's people that practice for Pi Day. Sometimes we have competitions. How many digits you can remember? In this book, it tells, let's see here. Oh, yes. Here is a pi, the pi eccentrics, people who like to memorize digits of pi. Hideaki Tomoyori. He had 40,000 digits of pi memorized correctly. Right? That's a lot, eh? How do you do that? You know what's crazy? I don't know what's crazier. Sitting there saying it took him to say it, it took him 17 hours and 21 minutes without making a mistake of just saying numbers. What's more insane? The person sitting there for 17 hours and 21 or the person checking them? You know how boring that? And you have to pay attention. Because you can't, sorry, what was that? Can you start over? No, they punch you. You're 15 hours in and the guy's like, I'm sorry, I dozed off there. Can you go back like 7 digits? But there's like, in this book that I have, there's people who have methods for remembering numbers. And, I'll find it. Some people take the English language and change sounds to numbers. I'll read this to you in a second. Here we go. So here are how to change sounds to numbers. Every time you hear a T sound or a D sound, because they sound similar, you think of a number 1. Okay? An N sound the number 2, an M sound the number 3, an R sound the number 4, an L sound the number 5, a J, a Ch or Sh, CH, SH, or J is the number 6. A K or a G is the number 7. An F or a V is the number 8. A P or a B, number 9. And a Z or an S is a 0. And then you can make poetry. For example, okay, how long would it take you to remember the following little poem? My turtle Pancho will, my love, pick up my new mover, Ginger. That seems like a sentence that doesn't make much sense, but if you have that sentence, let's see, how many is it? 60 digits of pi by remembering that sentence and the new sound thing. That's a lot of digits of pi in one little sentence. And then you just have to hear the sounds. So if you like have a whole 1,000-word essay, right? After Ginger, if you add my movie monkey plays in a favorite bucket, right? You get another. If you want 100 digits, you just have to ship my puppy Michael to Sullivan's back rubber. And you'll get 100 digits of pi in 3 sentences. But of course, you have to be really good at hearing sounds and knowing numbers, which might drive you crazy. Because every time someone says something to you, you now have like 584,352. Okay. So we can now go back to our notes and say, this is crazy that we now know there are 2 pi radians in a circle, and now you have an opportunity to switch between radians and degrees. 2 pi radians is equal to 360 degrees. If I divide both by 2 pi, I know that 1 radian is 180 over pi. And if 1 radian is 180 over pi, and I take that and type that into my calculator, I should get one more decimal place. 180 divided by pi. 57, oh, I had it wrong. My decimal places are actually wrong. 57.296. Rounded to 3 decimal places. So about 57.3 degrees, a little less than 60. 180 divided by pi is exactly how many degrees is in 1 radian. And you're going to be asked to switch back and forth between radians and degrees. So at the top of, oops, there we go. At the top of page 489. You have that a whole circle is 360 degrees. That's going to equal the 2 pi radians. From there, you get the following important formulas. 1 radian is 180 over pi. You could also figure out what 1 degree is. And since these are proportions, I'll put this one in a green box as well. Halfway around the circle is 180 degrees. Half of 2 pi is pi radians. So 180 degrees is pi radians. Now you had already learned from our math lab the other day that your arc length in degrees was the angle divided by 360, because that's the proportion of your circumference. Correct? That was the formula we came up with last week. That you can find an arc length part of the edge of a circle by doing a proportion, whatever angle you have, of the whole circumference. And now I can take this and I can take that formula and change it to radians. It's the same idea, but instead of using 360 degrees, 360 degrees is equal to 2 pi radians. So this is the formula for arc length in radians. All you did was change the 360 degrees to 2 pi radians, because that's the same. It's still a proportion of the whole thing. But mathematicians in this situation could not, I still like that form of the formula because it means something, but they were just too tempted. Can you see how much simplifies? Can you see that the 2 pi would simplify with the 2 pi? And you get a very simplistic formula if you're in radians. That simplistic formula is on your formula sheet. It is the first formula on your formula sheet. This seems like a good time to give you your formula sheets. So I'll hand them out. Recommendation for your formula sheet. I made it a different color so you could use it as a bookmark. Wherever we end, you can put your formula sheet in your notes. That way you find where we're starting the next day quickly. And we're ready for example 1. So to start, we want to get used to working in radians. So given 170 degrees, can you change this to radians? Okay. Some of you are going to remember the following formulas very quickly. I'm going to write them up here. Some of you are going to remember that 1 degree is pi over 81 radians. Some of you are going to remember that 1 radian is 180 over pi degrees. And a lot of you are just going to have the following two ratios available to you because that's where we started. We started off with 360 degrees was 2 pi radians. We started off with then cut them both in half. 180 degrees would be pi radians. These two formulas here, these two things, can help you convert from radians to degrees very quickly. So if I have 170 degrees, I'm going to need to multiply by, well, 1 degree is pi over 80. I'm going to need to multiply by pi over 180. And if I do that, I'm going to get 17 pi over 18. If you leave it as 170 pi over 180, you get full marks. You do not have to reduce your fractions. That's kind of nice. Okay. One of the ways, so sometimes when converting, you can multiply by pi over 180. Sometimes when converting, you're going to multiply by 180 over pi. Technically, here's the math that makes it really easy to remember which one you're multiplying by. When we do a conversion, when you change from one unit to another, right? How tall are you? 5'7". How tall are you? You don't know how. Okay, so how many is that? Okay, so if we were just comparing their heights and they didn't give me units, this person is almost 6 tall, 5 something, and that's 160. Giant versus little tiny person, right? Because the numbers, we got feet and we got centimeters. Obviously, the centimeters number is way bigger. Do you know how to change between inches and centimeters? Does anybody remember from grade 10? How many centimeters in an inch?
2.54.
2.54. So you would be at 5'7", that's 67 inches. I'd have to multiply those 67 inches by 2.54, and then I'd figure out how tall you are on centimeters. Or I could just steal your license, because it'll say that on there too, right? Okay. We have different measurements. We need to convert between them. When converting between them, the conversion rate, this right here, is saying pi radians divided by 180 degrees. What is 1 foot divided by 12 inches? They're exactly the same measurement, aren't they? So when you have the same thing divided by the same thing, that fraction is equal to 1. What happens when you multiply by 1? You don't change the answer. The answer is the same. But when we multiply by 1 in a conversion, we don't change the answer, we just change the units. And this is the easy way to remember. If I have degrees and I want to change to radians, wouldn't my degree symbols have to cancel out? So I need the 180 on the bottom because it's the degrees measurement. My degrees cancel out and I'm left with radians as units. And that works for every single thing, right? If you want to change from like inches to feet, you have 36 inches. 36 inches. I'll just write inches. What am I going to multiply by? Well, I want feet. I want my inches to cancel out. there is 1 foot is 12 inches. So I'd have to divide by 12 to find out this is 3 feet. And my units would go away, leaving me with feet. This is true for any conversion. You can use it for Canadian dollars to American dollars. You can use it for inches to feet, radians to degrees. You're always multiplying by something that's equal to 1. You just make sure your units of 1 cancel away, and then you're left with the units of the other one. So having that in mind, you should never mix up whether you're multiplying by 180 over pi or pi over 180. Yes,
Can you show us an example when you use 180 over 5?
sure. Part B, when we get there. Because we're going to change the radians to degrees. Give the exact measurement, 17 pi over 180. You could type that into your calculator. And we get 2.967 for 3 decimal places. Did it ask for 3 decimal places? No, it asked for the nearest hundred. 2.97 radians. Part B. We're going to do the second part first. We want to convert negative 12 pi over 11 radians to degrees. So if I have negative 12 pi over 11 radians, I'm going to multiply by 180 over pi, because my radians would then cancel out, to switch it to degrees. You could, okay, if I do 12 times 180, you would get full marks if you left your answer like this. Do you see that I just multiplied the top of my fractions and multiplied the bottom of my fractions? Most people will cancel out the pi's because they're obviously exactly the same. And if you're dividing, they would go away. And if I type this into my calculator, I get negative 196.364 degrees. The reason I changed it first, because right now, your brain works better in degrees than it does in radians. If I got you to sketch negative 196 degrees, would you agree that it's going in this direction? If you go past 180 a little bit further, this seems like a good estimate for negative 196 point. Did it ask me to round it to a certain decimal? Nearest tenth. 196.4. But we are also going to develop a way of thinking so you can do this as well. Okay? Halfway around a circle is pi. All the way around the circle is 2 pi. As a fraction, negative 12 over 11. Can you see that that's a little bit more than just the number part? A little bit more than negative 1. Because 12 is bigger than 11. So this would be negative 1 pi. And then if I broke this up into 11 equal sections, that would be going 1/11 more. That's where we're going to start thinking in that direction. Also, changing from radians to degrees, there is a shortcut when there's a pi involved. So I started off with negative 12 pi over 11 in radians. The shortcut is as follows. Did you notice that these would cancel out, that these pi's would cancel out, and you're just left with the 180? So the shortcut says replace the 180, replace the pi with 180 degrees, because pi radians is equal to 180 degrees. That's a shortcut that you will use quite a bit. And if you did that, you will get this 196 once again. Then part C, which we'll do quickly. Bell's gonna ring any second. We have 7.5 radians. I would multiply by 180 over pi, and then I would get how many degrees. So I take that to my calculator, 7.5 times 180 divided by pi, 429.7 degrees. Did it say to the nearest tenth again? To the nearest tenth. Circle questions 4, 5, and 7. Okay. And something interesting. In mathematics, radians is the only unit of measure that has no symbol for its units. When you have to write centimeters, you put a little cm to say centimeters. Degrees, you add a little degree sign. Radians, you write nothing. Right? You'll never forget units. However, if you forget units now with degrees, it's catastrophic. Because if you say the angle is 180 and you don't put the degree sign, you mean 180 radians. Which is about, like if I'm skiing, I might successfully fall attempting a 180. Because I'd only have to turn halfway. I'll probably fall after that, but that's okay. If you did a 180 radian, right, 6.28 is a full revolution. So that's like, that'd be like 29 turns in the air before you land. You just did a 180. No, you did not. You did a 180 degree. Because technically, if we don't say the units there, we mean radians, which is crazy. Yeah, new Olympics. Oh, AI could probably do that for me. I could take Olympic events and say, can you provide the commentary in radians instead of degrees? And then they would have to do like, instead of a 360, oh, that person just did a 2 pi.
That's probably like the original like thought. I don't think anyone else has ever thought of